In assignment 2, we built a complete B plus tree based DBMS from scratch with insertion, deletion, search, range queries, and a table and database manager layer on top. But that system had no transaction support. If an operation failed halfway through, partial data would remain in the tree. There was no way to undo the changes, and no guarantee that committed data survived the crash. Assignment 3, Module A, asks us to fit exactly that by implementing a proper transaction engine with full asset guarantees on the top of our existing B plus tree. We added three new files to our database package. The first is val.py, the write ahead log. Every single operation, insert, update, delete, is written to a log file on disk before the B plus tree is touched. This is the core durability and recovery mechanism. Each log entry stores the operation type, the key, and critically the value that existed before the change. This before image is what allows us to do undo operations. The second file is transaction-manager.py. This gives us begin, commit, and rollback. When you begin a transaction, every operation gets logged to the val and added to an in-memory undo list. On commit, the WAL gets a commit entry and the full database state is saved to a JSON snapshot on disk. On rollback, every operation is reversed in reverse chronological order using those stored before images. The third file is recovery.py, crash recovery. On startup, it reads the WAL, finds any transaction that has a begin but no commit, and undoes it automatically. So now what we do is to check our live test results, we open the terminal and run this Python file test_acid.py. We wrote 6 tests covering all 4 acid properties. Let me walk through each. So this is my test one output. This Python file test_acid.py. So in this we have written 6 test cases covering all 4 acid properties. Let me walk through each. So this is the test one of atomicity. We insert 2 rows inside a transaction, then roll back. The record count returns to 1 and both keys are gone. The B plus tree and the database manager record count are in sync. Neither shows the rollback rows. Atomicity confirmed. Now test 2. This is also for atomicity, but for a partial failure. We insert 1 row and update an existing one inside a transaction, then roll back. Both changes are undone, the new row disappears, and Alice's salary reverts to the original 70,000. Test 3. Consistency. We try to insert into a table that does not exist. A value error is raised before anything touches the WAL or the tree. No side effects, no partial state. Test 4. Durability. We commit 2 records, then completely discard the in-memory database, simulating a system restart. We reload purely from the JSON snapshot. Both records are fully restored. Committed data survives a restart. Test 5. WAL crash recovery. The most important test. We commit 1 record, then start a second transaction, insert 2 more rows, and simulate a crash. No commit is called. The WAL has a begin and 2 inserts for the transaction, but no commit. When recovery runs, it reads the WAL, identifies that transaction as incomplete, and undoes both inserts in reverse order. The count drops back to 1. Only the committed row survives. Test 6. Isolation. Two transactions are open at the same time. Transaction B inserts Bob and then rolls back. Transaction A inserts Alice and commits. Alice is present, Bob is gone. A rollback transaction does not corrupt or affect any other transaction. So to summarize, all 6 tests pass. To summarize what we verified, atomicity through rollback of both full and partial transactions, consistency through rejection of invalid operations before any state change, durability through JSON snapshot restore and WL based crash recovery, and isolation by confirming that a rollback transaction leaves no trace visible to committed ones. The Bplaze tree and the database record counts stay consistent throughout during normal operations, during rollbacks, and even after crashes. That is exactly what assignment 3 module A required.